So I'm going to talk about a couple of things. I got a couple things on subgrouping, but not much. But I'll talk about paths real quick because paths are a really common thing that we're going to talk about when we're talking about graphs. So one thing basically is that when we actually create our graphs, we can talk about moving through them via paths. So I'll kind of go over this a little quicker then. Say, what kind of problems can you think of where finding a path matters? And we kind of talked a little bit already. It's like Google Maps, social networks, right? You can even talk about, like, if you're talking about states, like I just mentioned about like that, Roomba, for example, you can talk about saying, what's the most optimal path it should do, as it's kind of like, what's it called? As it moves forward. Those are kind of something similar to something called PGMs. What's that? Oh my gosh, I'm bringing the term for this, probabilistic graph models. And so the idea there is that maybe there's certain chances, there's certain things to go in certain directions. So it might be good to figure out what the optimal path is from there. Okay, so some kind of like, again, focusing on relationships, but some possible things we can talk about are things like when you need to find the shortest path, when you need to visit certain nodes. So imagine like you're on like a delivery route and you have to hit every individual house, right? But you also don't want to just like go randomly through the whole graph, right? You want to kind of make it shortest as possible. There's other things like, can you visit all nodes? Is it possible to actually go through all this stuff? There's some really interesting problems you can kind of create with graph theory and everything. Okay, so those are kind of like I think a good thing to kind of think of is like, being like, okay, we should learn what graphs are, but like, when does it actually matter, right? We can kind of think about that stuff. So I will talk about, just very, very briefly, just mention is that finding shortest paths. This is a much more computer science, mathematics focused part, but it's important to kind of know that this thing exists and what you can do. So when you're finding shortest paths, some ways we can kind of relate to, like, when does a short path matter? You can think of like web scraping. So imagine if you're going, you're web scraping and you're just going to go by each link, right? And so you go on a website and you find a link and you have your little crawler, click on it, go to that web page, click on the next link, click on the next link, click on the next link. You have to determine, like, how do you want to traverse, these linked pages and everything like that. So you might want to figure out what the shortest path is or the best way to scrape in this way. So maybe you need to pull the information out first, or, can you have a graph that's already pre-built, or do you build the graph as you're going through it? So a whole bunch of things you can think about. The curriculum also mentions about searching files, in particular JSON. You can think of JSON really just building up graphs, right? Is that a JSON object really has, so a JSON file, right? So if you remember, right, do you guys know JSON, right? Like our thing. So remember, JSON can have like either like a value, right? Or it can have something like a key. And then it can also point to another JavaScript object, right? And so you can essentially think of these as like different points where you can go from this key to here, and maybe inside here, there's another object. So you can kind of see like this is kind of pointing inward. So like, how do you traverse a JSON object kind of deal, or JSON file? So this can be also an important part of like, how do you make that connection between there? Again, because JSON has those relationships built in. Another one is internet traffic. So saying, like, how people are going to be connecting with each other, in the sense, or not connecting with each other, but connecting to services and stuff like this, and saying what's the best path going forward. This again can be a whole bunch of different things that again can be very much related to computer science by itself. Okay, but since finding shortened paths is usually a really important part, it's important to kind of mention about a couple of algorithms. So the first algorithm that's kind of mentioned, I think it's the only algorithm that's mentioned in the curriculum about shortest paths, okay, is, sorry, I always mess up this IJ, it's Dijkstra, I think that's right. So it's Dijkstra's algorithm. I don't know if I'm overpronouncing that, but the idea here is basically finding the shortest path. So you can look it up on Wikipedia. I went to find this online that I thought was pretty good. And this is where it's kind of interesting. It kind of remembers where it's been, and it's a relatively fast algorithm. There's some disadvantages to it compared to other searching algorithms, but usually this is like the go-to one. So if you're going to remember any algorithm about searching through graphs, I would suggest, going through this part. There's also a really great YouTube video by Computer File that kind of talks about it, like saying like, what's going through. Most of their videos like 10, maybe 15 minutes at most. It's like a 10-minute video. And he talks about going through like traversing a different graph. You can see here, you can see like this graph right here, and he talks about the different weights and saying, you know, like how do you connect and find the shortest path? So you can imagine like this can be a really tough problem, right? Because you don't want to try every single path. Turns out that will explode very quickly trying to find every single path. But Dijkstra's algorithm does a pretty good job of doing that relatively efficiently without very much storage and stuff like that, remembering a bunch of paths. Okay. So that's a good one to have. An improvement to that is A star. So you'll usually see it like A, like asterisk like this, and it's usually read as A star. It's another search algorithm. It's a little bit of an improvement to Dijkstra's, but it does basically, the disadvantage is that it has to store more information. So it's another interesting one. And again, they did a follow-up video. You can see it right here, A star video about this algorithm. So I would definitely suggest, you know, definitely watching this one. You could watch this extra one and check it out. Okay. So anyway, it's an important subject to kind of go through, but I'm not going to go through the whole algorithm because there's not a reason for us to go through that whole thing. If you guys would like, we could, but anyway, that's about finding the shortest paths. Any questions or anything come to mind? No? Okay. And so the last one that I'm going to mention about is really about this clustering subgroup stuff. And I'm not really going to go into detail because I think the curriculum actually does a pretty good job kind of going through all the different ways to cluster it. But the thing I really wanted to point out is basically the idea here is that we can clearly see that there are like 3 groups here in this graph because it's not fully connected, right? Or not fully connected, it's not connected. So you can see here, it's like, okay, like this is clearly a group here. But in this one right here, like if I were to say like, okay, like break this group into smaller groups, like, I don't know, does anyone have like an idea, like just looking at this by itself without talking about any algorithms, like where would you like say is another group? Like I would say there's at least like 2 groups in here, if not like 3 that I can kind of immediately identify. Anyone got a suggestion? The way you can think of this too. Oh, go ahead, Jenny.
Well, that the folks who are up at the top, Preston, Colin, Yang, Owen, they seem like they're only connected to everybody else through Altman. You know, that like if Altman were to go away, these people would be isolated from everyone else.
Yeah, so you can kind of see like these guys probably are like, you think of it this way too, is Preston here is much more related to like Owen than Avery is to like Owen, right? So you're like, okay, it kind of looks more here versus over here, even though Avery might be kind of further away from like, let's say Olivia, they seem a little more connected than how these guys are because of that Altman right here. So that's kind of the idea here. I would probably say if I had to like very quickly say like, oh, what would you say are like 3 groups here? I'd be like, okay, this is probably like one group by itself over here. I might call this maybe another group, you know, by itself, depending on like how that's connected. And then like this like last one's kind of like this very cluster group. But like it depends exactly how you go through it. And that's the idea where you can, what Jenny was saying is like kind of looking at Altman, saying, oh, if you got rid of Altman, they kind of get separated. The idea here is that you remove edges that would kind of separate them out the most. And so, for example, this is from the curriculum. So you can see there's 1, 2, and then there's that 3rd group here. We can split that 3rd group essentially into this next one by removing just 1 edge. I think Altman to Nancy was what was removed. And then if you remove 2 edges, well, then we can disconnect this one. So kind of similar to what I said, right? It's like kind of off to the side here. And then you can start seeing if we break it up into further, in this case, 3 edges. I don't know what, oh, this part was removed. You can start breaking this up. So the idea here is like you can start breaking them into different clusters and stuff. And this is kind of like similar to the k-nearest neighbors and stuff like this, where you're saying, okay, like these are my different groups and stuff like this that are more similar to each other because they're closer together. And remember this weight here. Note that we can also, if these edges were weighted, we could do the same thing, where the edges, if they're longer, if they're bigger, for example, it just means they're further away. So we can also add that into their part of this kind of like idea of like removing an edge. Okay. So I want to kind of mention a little bit of that because it's an interesting problem that is definitely got a difficult like way to mathematically describe this in a way that's concise and consistent. But there's definitely some solutions that you can do and everything. But you can imagine if you have a really high complex graph beyond just like, for example, if you have certain edges that each edge represents, maybe if they like something versus this like something, or different relationships, you might actually have multiple edges that connect different parts and stuff like that, and you have to determine how to trim those. So graphs can get very complex very quickly, but yeah. Okay. Yeah, that's kind of all I really have to talk about for graphs or anything. Do you guys have any overall questions or anything that you guys hit, especially Andy and Jenny, as you guys kind of hit on the section, and like how it relates to or anything like that?
I have a question. So like when you're making like like different clusters and stuff like that, what's like I know kind of in the curriculum it's just kind of like, okay, do these kind of different ways of making clusters, and then which one do you think is better? And then like the answer is just kind of like, well, this one looks visually better, but like is there like a way to like actually be like, this one is maybe better than this one because of this certain metric?
Yeah, so one thing you can do is you can treat this, so like if you remember, like let's forget about graphs for a second, right? And if you remember, we had in clustering, we had like points. Oops. We had points like this. And like we could measure it with some distance metric, right? Saying how far away these different points are. You can use the graph to say how far is Altman away from Colin, how far is Altman away from Avery, and that can be kind of a metric of saying like, what's the distance between this part. It gets a little tougher in the sense of being like when we're removing an edge like this, we're not really saying like, oh, Altman and like Nancy are very far apart from each other. It's like, oh, they're actually really, like, they might actually be closer together than Preston and Altman over here. So the idea is you're trying to find a metric here together that's going to, how do I say this? That is describing the relationship of this over just like one individual connection. So you could technically try to use like, kind of like this clustering, like the we've done like clustering algorithm with distances. This is where it gets very like I think the mathematical formalism feels very fuzzy sometimes. Like this is where I like relate this back to topology. And so like one of these problems, for example, that can feel very like not like mathematical is something. Have you guys heard of like the 4-color problem by chance? No. Okay. So there's a theorem that says if you have any 2D, like map of countries that are all touching each other, you can always color the graph such that you only need at most 4 colors so that no 2 countries of the same color are touching. Which when you hear that, it doesn't sound very mathematical by it's like, like kind of thinking about this, it looks very visual, but you can describe this actually with graphs and essentially using the relationships of touching as edges and then the countries themselves as nodes. That's kind of like how I kind of imagine this part is that it takes a little bit of creativity and like trying to find what that metric should be and that what you're trying to minimize. I personally don't have a huge amount of experience in like doing more graph problems just because it's not something I run into quite often. But yeah, sometimes also it's like, what is nice is that we do have like a visual sense of like what's going on here. But of course we should always be careful with that, right? Which I think, Andy, what you're trying to get at too, right? It's like, you can't just simply say, oh, it looks good, because it can be a very complicated graph can look too complicated in the sense that you're not gonna be able to visually get any real meaning from it.
Yeah, I mean, I know they went into like betweenness and closeness and the eigen values and all that. It just feels like you'd almost have to have like a certain threshold or something beforehand to even like make the clusters that you want to measure.
Right. You're sort of saying like that threshold of like, what you tune it to, like how
yeah,
you kind of know.
Because obviously you can narrow it down to just each one's its own cluster, but that's not useful. And then if they're too big, then maybe that's not useful either.
Yeah, I would say the general rule, which tends to also look at like how visually it looks, is the simpler the better. So if you can turn up the threshold where like you're only removing like one edge, 2 edges, like that is more preferred than if you're turning up the other direction, if that makes sense. But yeah, I think a lot of it, honestly, is more intuition than direct like numbers. Okay. Cool. All right. Well, we are out of time now. So just a reminder, I guess stop recording it here if you guys are cool.